Hi everyone, welcome to our next topic, which is circular motion, so things going round in circles. Okay, starting specifically with what's called the horizontal plane. So this is working in 2D with things that are going round like on a tabletop circle or on a bit of string going round your head. So not in the vertical direction like a roller coaster loop-de-loop, or a Ferris wheel. That's the vertical plane. Talking the horizontal plane. Okay, probably easier if I showed a diagram. So look like that little man there. Look, the actual circle is parallel to the floor. It's horizontal. The ball's height is not changing. It's just going round and round in a flat circle. Now it could be on a string like he's doing there, or it could be on a tabletop. It could be a car going round a bend. Okay, on a flat bit of road. Okay, anything like that. So we start with the horizontal plane. And what you'll need to do is to draw me a circle first of all, reasonably big, so we're going to be adding stuff to it. Okay, so this is looking down from above now, a bird's eye view of a particle of mass m going round in a horizontal circle, a flat 2D circle. Okay, and it's got a radius of r. Pause the video if you need to add some extra notes in. Okay, and what we're interested in here is two things. What's called the angular speed, okay, the speed with which it's rotating round, okay, and what's called the tangential speed, which is like the actual speed that the object is travelling at. You've got to be careful not to use the word velocity here, because velocity depends on direction, and if you're going around in a circle, your direction is constantly changing. So we tend to use speed rather than velocity. Okay, so if I add on to here an arrow, because if you imagine what would happen if you were spinning around on a string and the string suddenly broke. Well, the object would fly off at a tangent, okay? And its velocity would be equal to the speed it had at the point that the string snapped, okay? So we call it v, because if it did fly off in a straight line, it would have velocity, but it's actually equal to the speed at which this particle is traveling around the circle, okay? So v is what's called the tangential velocity or speed, okay? So I'll put speed there as well. Now, to find that speed, what we need to do is a little bit of arc work, because speed is distance over time. And so if this particle, if I can grab it, there we go, if this particle was here and it moves around the circle to here, if we know how far it's travelled and we know how long it took, we can work out its speed. Okay, now how far it travelled depends on the arc length, and the arc length depends on the angle. Okay, so normally we measure angles in degrees, but in this topic we don't use degrees for the angle. We've got a different system of measuring angles called radians, which you'll come across in a lot more detail when you come to it in pure maths. Okay, but in radians, it's not that complicated really. In radians, one full turn is 2 pi. Okay, is 2 pi when you work in radians. So 2 pi radians is equal to 360 degrees. Okay, it makes working with trigonometry easier, and it makes doing arc length calculations and things easier if you work in radians, okay, rather than degrees. So one full turn is 2 pi radians. So when you're doing this circular motion, you've got to make sure that you're measuring everything in radians, not degrees. Okay, it doesn't make too much difference to you otherwise. But 2 pi is what, 6.28 roughly, and so that would be one full turn, okay, if it was per second maybe. So one full turn would be 6.28 radians per second, per minute, whatever. Okay. Now, how does that make things easier? It's easier because what it does then, if you work in radians rather than degrees, arc length is theta r. Okay, is that arc length there? So the distance that this red particle has travelled is theta r. Okay, so if we say that speed equals distance over time, working in radians, the distance is theta r, and the time, let's say, is just t seconds. And then what we say then is that if you do theta over t, so how quickly you're turning, your rate of turning, okay, are you doing 1 full turn per second? Are you doing half a turn per second? Okay, is it 10 full turns per second? Obviously all in radians, so 10 full turns would be 20 pi, because 1 full turn is 2 pi. So the rate at which you're spinning, okay, is called angular speed. Okay, and it has the symbol, the Greek symbol omega, like a curly W. Okay, so angular speed is theta over t, and so what we get then, our tangential speed, v, if you put theta over t as omega, you get r omega. Okay, and that's a really important formula. So v, the speed at which this particle is actually travelling in meters per second, is the radius times the angular speed, and the angular speed is theta over t measured in radians. Okay, and then we can try some questions just using that formula there. So pause the video if you're not quite ready to move on. Okay, and you'll get used to working in radians. Most questions you give your answer in radians anyway. There's the odd question which you've got to go between degrees and radians, and I'll show you an example like that. Okay, so if we have a look at some questions then, remembering that v equals omega r, and the unit for omega is radians per second. So if I put over here radians per second, so rad s minus 1. Okay, for question 1 then, a particle moves in a circle of radius 2 meters with a speed of 3 meters per second. Now, because it's in meters per second, I know that that's the tangential speed, the velocity v. Okay, so 3 equals, well, the radius is 2, so 2 omega, and then to find omega, it would be 3 divided by 2, which is 1.5. Okay, radians per second. Now, when you're not familiar with radians, that doesn't mean a lot. Okay, pi is a half turn, and pi is 3.14. So we're looking at roughly a quarter of a turn per second. 1.5 radians is roughly a quarter, just under a quarter of a turn. Okay, you can change it to degrees. You just got to times by 360. Well, put it over 2 pi and then times by 360. We don't need to do that. Okay. Number 2. The tangential speed v of an object is 8 meters per second, and its angular speed omega is 4 radians per second. Calculate the radius of the circular path. Okay. Now, if you imagine, if I've got 2 objects, and one is on a short string and one is on a long string, their angular speed can be the same. So they both complete 1 full turn in exactly the same amount of time. But the longer string, particle on the longer string, has actually gone a lot further, because the longer your radius, the longer your circumference. Okay, so 2 objects can have the same angular speed and have different tangential speeds, because it all depends on radius as well. So for this question then, v is 8, so v is omega r, and v is 8, and omega is 4, so 4r. So for this to be true where v is 8 and omega is 4, that can only be true if the radius is 2 meters. Okay. If you lengthened the radius and kept the angular speed the same, the tangential speed would have to increase because it's got a bigger circle to do in the same amount of time. Okay, so the difference between angular speed doesn't really, not affected by the length of the string, but tangential speed is the radius of the circle. Okay, let's have a look at the next one. An athlete runs around the semicircle bend of a track, so one complete semicircle in 12 seconds at a speed of 7 meters per second. Okay, so V is 7. We don't have the radius. Okay, what we're going to do on this question is we're going to find the radius. Okay, so I should put that in there, shouldn't I? So find the radius of the track. But we don't have omega. Okay, we don't know the angular speed yet. So that's the first thing we're going to have to work out. So if I do a little sketch here, this is a semicircle. Okay, R. And the angle, now remember I said earlier that a full turn in radians is 2 pi. So if this athlete has completed a semicircle, then she's completed an angle of pi. 180 degrees, half a full turn, is pi radians. Okay, so theta is pi rads, and she did that in 12 seconds. So to work out omega, we need to do theta over t. So omega is pi divided by 12. She turned pi radians, it took 12 seconds, so to work out her angular speed in radians per second, we divide by 12. Right? Now we can use the formula V equals omega r. So 7 equals pi over 12 times r. If you multiply 7 by 12 and then divide by pi, you'll get that the radius must be 26.7 meters. Okay, that's a little bit tricky having to find omega yourself, but omega is the angle that you turned divided by the time that it took. Make sure you're working in radians though. Okay, and a half turn is pi radians because a full turn is 2 pi radians. And then this number 4 here is quite tricky because it's in sort of totally the wrong units. An aircraft with speed of 70. Okay, so V is 70 meters per second, which is about roughly 250 kilometers an hour. Okay, or about 170 miles an hour. Turns from a bearing of 50 degrees to a bearing of 170 degrees. Now, you don't need a drawing, but if you go back to bearings from year 7 or year 8, it was on an angle of 50 degrees there, and now it's on a bearing of 170 degrees, which is down there. The most important thing is the angle that it turned, which is 120 degrees. Okay. Now then, to convert that into radians, well, first of all we say that it's 120 out of 360, which is a third of a full turn, isn't it? And it's a third then of 2 pi, because a full turn is 2 pi radians. It's 1/3 of 2 pi, so 1/3 of 2 pi, the nicest way of writing that would be to write that it's 2/3 pi. Okay, so that's our theta, and it took 10 seconds. So to work out omega, we do theta, which is 2/3 pi, divided by 10, and probably the nicest way of writing that is to write it as 2/30 pi. So now we've got lots of information. We've got V, we've got omega, and all we've got to do now is find the radius of the turn. So V equals omega r. 70 equals, so this is our omega, 2/30ths of pi. We don't know the radius, so if you work this through now, so multiply by 30, divide by 2, divide by pi, you should get a radius of 334 meters on the turn. Okay, and what the plane's done is it's gone round there. Okay, so they're quite tricky, those last two. Okay, normally in a question you'll be already working in radians, or you'll be given the angular speed, in which case it naturally comes out in radians. It's helpful to have a rough idea in your head of what radians are. Okay, so 2 pi, 6.28, is 1 full turn. So if you're doing 1 full turn per second, you're doing 2 pi radians per second. Okay, half a turn is pi, so just over 3, isn't it? Okay, a half turn is pi. Right, okay, moving on then. Now we'll look at the forces involved in keeping this thing travelling in a circle, because we know that if the string snaps, it will fly off in a straight line. So the only thing stopping it from flying off in a straight line must be some sort of force pulling inwards, and that's exactly what the string is doing. So if you want to do a fresh diagram for this one, okay, what we have at all times is a force acting inwards. I wish I hadn't picked green now. A force, okay, which if it's a string is in this case would be tension, but it's not always attached to a string. Sometimes it's like the friction of a surface. But there's always a force acting on the object, stopping it from flying off. Okay, you may have heard the words centrifugal, centripetal. Okay, centrifugal is if you've got something spinning around really quickly in a container, and centrifugal is the force that the object puts on the container. Well, centripetal is the opposite. Centripetal is like the force acting on the particle to stop it from flying off in a straight line. So you could say that the force in the string is a centripetal force. We don't tend to use that language very often though, okay? But there is always a force acting towards the centre of the circle. Now if there's a force and there's a mass, Newton's second law says there must be an acceleration. Okay, now you don't need to know the proof for where this comes from, okay, but the acceleration, and bear in mind because the force is towards the centre, so is the acceleration, okay, because this is what's causing the thing to be constantly changing direction and not flying off in a straight line. The acceleration, which is always towards the centre of the circle, is given by r omega squared. Okay, you can look up a proof if you want. You don't actually need to know the proof for this. Okay, so the acceleration is given by r omega squared. Now remember that omega is theta over t, is our angular speed. Okay, how quickly we're turning. Also remember that v is omega r, which means that we can write an alternative version of this formula, okay? Because if I write this as omega equals v over r, I can write this same formula and take omega out and put v in instead, because sometimes in a question you'll know v, sometimes in a question you'll know omega. So that would be r times, so omega squared would be v over r squared. So v squared over r squared. Okay, square the top, square the bottom. That's going to cancel with that. And what you end up with is just v squared over r. Okay, so there's two versions of the acceleration formula. Okay, always towards the centre. If you're working with omega, it's just r omega squared. If you don't know omega, but you do know the straight line tangential speed, then it's v squared over r. Probably worth highlighting all these formulas. Okay. And then, well, Newton says that F equals ma. And so to find the force in the string required to keep this thing going in a circle, you've got two options. You can either sub in A as r omega squared, and you get m r omega squared, or you can sub it into v squared over r. So F equals m, and then instead of a this time, I put v squared over r, mv squared over r. So there's three formulas on this page, okay? You've got acceleration in terms of omega and r, and then F with m omega and r. Then you've got the alternative, which is if you're working with v rather than omega, the acceleration is v squared over r, and the force is mv squared over r. It all depends on what you're given in the question, which one you'd prefer to use. Obviously, if you use this formula up here, you can easily convert from one to the other anyway. Okay, so it doesn't really matter. Okay, but just so you know that the force from the string or the force from the tabletop, whatever is holding this thing in a circular path, always acts towards the center. The acceleration is always towards the center. So if the red particle was down here, the force would be going this way, and the acceleration would be going that way. Okay, and that's what keeps it in a circular path and not flying off. Okay, so let's have a look at some questions of that. So a particle of mass 0.3, so m is 0.3, is attached to a light inextensible string, so I don't have to worry about the weight of the string as well, okay, of length 0.6, so the radius is 0.6. The particle moves with a speed of 4 meters per second. Calculate the tension in a string. So it's going round in a circle. V is 4, the radius is 0.6, and m is 0.3. And we've got to calculate the force in the string. So how much force does it need to keep this particle from flying off? So, very simply then, we know V is 4, m is 0.3, r is 0.6, so we can just do F equals, now we're working in V not omega, so I'm going to use F equals mv squared over r, so 0.3 times 4 squared over 0.6, it needs a force of 8 newtons. Okay. So the force in the string is 8 newtons, and as long as the string can hold 8 newtons, not a problem, we can easily do this. Okay. Right, part B then says that the maximum tension in the string is 30 newtons. So any more than 30 newtons and the string will snap. So calculate the maximum speed and angular speed of the particle. So we're being asked to find V, and we're being asked to find omega, which is easy. Once I've got V, I can do V equals omega r at the end, and I can find omega, not a problem. Okay, so what have we got then? The force this time is 30, so we've got up to the max. We still know the radius is 0.6, we still know the mass is 0.3, so if we find V first, so if I use F equals mv squared over r, 30 equals 0.3 times v squared over 0.6. So to rearrange that, you need to times the 30 by 0.6, divide it by 0.3, and then square root it. You should get a velocity of 7.75 meters per second. Okay, so that is the fastest that this particle can travel. Any faster, the string will snap. Okay. If I convert that to an angular velocity, so V equals omega r, omega equals V over r, which we saw on the previous slide when we made our second version of the formula. So that's 7.75 divided by 0.6, that's 12.9 rads per second, s minus 1. Okay. Now, what is that in real life? Well, remember that 1 full turn is 2 pi, so 6.28. So 12.9 is just over double that. So you're spinning around just over 2 full rotations per second, that means. Okay, 2 rotations per second, 2 full turns per second. Okay, normally we give it as revs per minute. So if it's 2 revs per second, it's just over 60 revs per minute, 60 RPM. Sorry, 120 RPM. What am I on about? Okay, so if you ever want to think like, is that a realistic answer? As long as you know that 2 pi is 6.28, and that means 1 full turn. Okay, so this stone is going around. If it's a stone, it's going around 2 full turns per second. The speed of the stone is 7.75. So if the string did snap now, it would fly off in a straight line with a velocity of 7.75 meters per second. Okay, and I've got one more example. A train of mass 45 tons is travelling at constant speed v around a circular bend in the track. The radius of the bend is 550 meters, and the acceleration of the train is 0.22 meters per second. Okay, but there's a bit confusing here because it says in the start of the question that the constant speed v, okay, but then it also says it's accelerating. But remember, when you're travelling in a circle, even at constant speed, you are accelerating towards the centre. So it doesn't mean that the train's getting faster. That's the acceleration towards the centre that's keeping it going round in a circle. Okay, so m is 45 tons, which is 45,000 kilograms. A is 0.22, R is 550, and what we've got to find is the speed of the train, so v. I know we don't call it velocity, but we still say v, because if it flew off in a straight line, it would be velocity. Okay, so how are we going to start this off? Well, if we're trying to find v, it probably makes sense to use the acceleration formula that's got v in. So the acceleration is v squared over r. That's one of the formulas we had in a box earlier on. So 0.22 is v squared over 550. If you times by 550 and then square root, v comes out nicely. It comes out as 11. So that's 11 meters per second, roughly 30 miles an hour. Okay, round the bend. What assumptions have we made? Well, the train is a particle, there's no wind, anything like that, okay, and we're ignoring things like friction and possible changes of speed as well. Okay, so the speed is 11. Then it says find the horizontal force applied to the train by the rails to keep it on the track. So looking down from above, remember, as this train is going around the bend, okay, that way, there is a force acting inwards towards the centre of the curve, okay, and there is an acceleration inwards towards the centre of the curve. Otherwise, the train would crash off the track into whatever's next door. Okay, so we don't want that to happen. Where does that force come from? Well, it's the rails rubbing against the side of the wheels. Okay, I don't know if you've ever seen a train wheel. It sort of looks like that. Okay, and the track is there, and it pushes sideways on it. Okay, or if the train was one to go the other way, there's one on the other side, exactly the same look, like that. Okay, and it's this force here which stops the train from flying off the track when it comes to a corner, that little interface there. Okay, normally you've got, like, obviously the weight of the train acting downwards on the top of the rail, but there's also this sideways here. Okay, so that's the force that keeps it going around the bend. So using F equals mv squared over r, because we know v from earlier on, it's 45,000 times 11 squared over 550, 9,900 newtons. So it's a massive force, sideways force, needed to keep the train on the track and not flying off in a straight line. Okay, and that force, like I say, is between the rail and the wheels of the train. Okay, and we'll stop there for today.